So we're going to keep going with chapter 3, and you've been reading about Tycho Brahe, and he was the data scientist of his day. So he was a forerunner in data science and in data quality, and he wrestled with both the polemic and the Copernican models. He's a mathematician. He's from Denmark. He grew in fame because he recognized a supernova in 1572, and he measured distance to a comet that came soon after that, two big events. And for that, the King of Denmark really recognized his genius. And the King of Denmark was willing to buck the astronomers of the day who were saying that the supernova and the comet both had to be in the spheres that were very closest to Earth, right with the moon. And they had to be in that sphere right with the moon because the heavens are unchanging. And this supernova and this comet were dramatic changes, so they had to be close by. Now, Tycho saw things differently. His measurements said that there's no way that this supernova and no way that this comet could have been close by. And number two, he never saw parallax with either one of those events. And again, parallax is the apparent movement of the object when you, the observer, change locations. And you are looking for that apparent movement against the backdrop of what's in your background. So the thing that we talk about is the thumb moving relative to the trees in back of you. Okay? Tycho said two things. My measurements tell me that the supernova and the comet are much farther away than the moon. And number two, I am not seeing parallax as I do with the moon, so therefore it cannot be in the moon's sphere. And he challenged the astronomers of the time who were saying that. And the King of Denmark liked the challenge that he was proposing. And because he liked the challenge that he was proposing, the king gave Brahe an island off the coast of Denmark where he could build an observatory. He called the observatory Uraniborg, which sounds like the later planet that was discovered. They both come from the same Greek root, Uranus, which means the heavens. And at this observatory, Brahe created devices and instrumentation that he could use with the human eye to take very precise measurements. So in taking those precise measurements, he came up with a precision factor that was within 1/2 of a fingernail. So it's about 1 arc minute, less than 1 arc minute. And that's very accurate. For the day, for that time, accuracy was within about within about 4 arc minutes, or about 2 fingers. So this was much more precise. And in doing so, he was looking at the stars, and he was looking at tracking what those bright stars were relative to the farther stars away. And he was not seeing parallax at all, even with his very precise measurements. He ended up with a model that was a fusion of Ptolemaic and Copernican models. He fused them both. So he said, I'm not seeing parallax, so therefore the Earth must be motionless, and therefore the sun must revolve around the Earth. But I'm going to go with Copernicus on the fact that all the other planets revolve around the sun. And that's what you're seeing here, this very convoluted off-center model that has all of the other planets rotating around the sun, and you have the sun rotating around the Earth. Now, this is very messy. nobody went for it. He was kicked out of the Danish court because of it. Not a good time to be kicked out of the Danish court, because the Danish court was very tolerant and the Catholic Church was not. And in fact, there were burnings at the stake for people who were too loud about Copernicus. And Giordano Bruno was one of the friars who was very vocal about Copernicus and was burned at the stake in 1600. So not a good time to be without your court that you were working in. But Brahe wound up in Prague, and when he went there with all of his data, he took on a student, Johannes Kepler, who was a German mathematician. They argued. The Dane and the German, very different mindsets, but they both recognized the precision and the accuracy of the data. And when Brahe died, just a year later, 1601, he willed the data to Kepler on his deathbed and said, please analyze it and find the patterns. Kepler went on to become the imperial mathematician of the Holy Roman Empire. Kind of a tight spot to be in, because you got to toe the line against Copernicus. Kepler kept a low profile, analyzed and analyzed and analyzed for years while he was the imperial mathematician. And he also went on to do additional measurements of planetary orbits. And in doing those measurements as accurately as Tycho had done them, he worked on the calculations more. And he calculated each planet's distance from Earth, which he had, but then he figured in that Earth was revolving around the sun, a la Copernicus, not stationary and not motionless. So that got a little complicated. And then he also calculated each planet's distance from the sun, which he said was stationary. Now, that was very difficult because all of these measurements were taken from the Earth while the Earth is revolving around the stationary sun. These calculations took years. When he was done with them, he was very, very close to to Kepler's original calculations. And he developed circular models for that. But if you think about it, that's your third hint that something's awry. Because if it takes you years and years and years to fit these calculations to a model, then something's not going right. And he predicted it very, very well. But when it came to the rotation, the revolution of Mars around the sun, some of Brahe's original measurements were 8 arc minutes off. And that's about 4 fingers. And that's not a lot for an entire orbit over the course of a year for Mars. But Kepler trusted Brahe's accuracy. And he said, I can't fudge this. He has a very famous quote, if I had believed that you could ignore those 8 minutes, I would have patched up the hypothesis. Many scientists do. But since it was impossible to ignore because it was so far off of Brahe's accuracy, those 8 minutes pointed the road to a complete reformation in astronomy. And by trusting his gut, Kepler changed astronomy and changed the world order. He found that that instead of a circle, he started and sketched out. Remember, all great scientists start with a sketch. And he sketched out all of the points as accurately as they were. And they formed just a touch of an oval. Remember, an ellipse can be a circle, and it can be an elongated oval, and it can be in between. These ellipses that Kepler was sketching out were just like 1 to 3 degrees off of a circle. just a touch off in an ellipse. And that opened the way for the orbital period to be very precisely on. And it explained a lot more about the varying speed of the orbit. So in doing that, in making that sketch, that led to 3 laws that Kepler wrote mathematically to describe the data that Brahe had willed to him and the data that he had developed himself. Let's talk about what a scientific law is again. A scientific law is a description of phenomena, a description of these orbits in a mathematical pattern. And so, you've heard of examples of it. Newton's second law, F equals ma, mathematical. You've already learned ideal gas law, PV equals nRT. Oh, sorry about that. I'm thinking my meteorology class. You didn't learn PV equals nRT. Maybe you learned that in chemistry in high school. If you take my meteorology class, you can learn PV equals nRT. But these are mathematical constructs that explain phenomena. And that's what Kepler did. So let's go into that in the next video.